The very first simultaneous move game that we took a look at was an example of a prisoner's dilemma, and remember that these occur in non-cooperative games. The Nash equilibrium that we get under a prisoner's dilemma is inferior to another outcome that could be achieved with cooperation. So in effect, both of the players get an outcome that is inferior to one that could have been achieved if both of the players could talk with one another. So if we took a look at Paola and Diego, remember that the best outcome for both of these was $2 for each player, but under the Nash equilibrium, they ended up only getting $1 each, and that $1 each is a vastly inferior outcome to $2 each. So that is seen as a prisoner's dilemma. We see prisoner's dilemma. It's a very special case of a game theory game, and there are a lot of applications for it. We do see it in international trade disputes, political campaigns, legal disputes, and competitive business pricing. However, there's always one classical example of a prisoner's dilemma that always seems to pop up, and that's where people are going to be jailed and seeing exactly how much time they're going to be serving. So I've actually drawn up the classical prisoner's dilemma right here. We have two players. We have Christopher Maloney and Mariska Hargitay, and they have two strategies each to either confess to a crime or not confess to a crime. So this is exactly for you Law and Order fans out there. And the story behind it is both of these players are being accused of a crime. Both of them are being held in their own little interrogation cell, like you see on the TV shows or on the movies quite often, and they cannot communicate with one another. So Chris cannot talk with Mariska and vice versa. And the police officers in question are trying to grill them about a particular crime that happened, and each of these players has the option of confessing or not confessing to the crime. So let's go ahead and see what the Nash equilibrium is going to be using the best response technique. Here the payoffs are going to be years in prison. So we actually want fewer years in prison. Each of these players wants fewer years in prisons. So this is actually one example where the lower number is going to be the better payoff for each of the players. So 1 year in prison is preferable to 2 years in prison, which is preferable to 3 years in prison. Of course, each of them wants 0 years in prison. So when we go ahead and do the best response technique, we can do the same sort of methodology. Pretend that you're Chris. You know for sure that Mariska is not going to confess. What's the best thing for you to do is to go ahead and confess, because that will give you 0 years in prison. If you know that for sure that Mariska is going to confess, the best thing for you to do is confess as well. Do the same thing. Put yourself in Mariska's shoes. What are you going to do if you know for sure that Chris is not going to confess? You should go ahead and confess. And then if you know for sure that he's going to confess, you should confess as well. So each of these players has a dominant strategy to confess, and that leads us to the Nash equilibrium right here, where both of them confess and they end up getting 2 years in prison each. So this is the Nash equilibrium. However, this Nash equilibrium is going to be vastly inferior to something else. It would be vastly inferior to this 1 year for each of these players. Both of them would much have this 1 year in prison each rather than 2 years in prison. So therefore, this is what makes up a classical prisoner's dilemma, or just the prisoner's dilemma itself. If they were allowed to cooperate with one another, they would go ahead and hone in on this option right here, but because they are not able to cooperate, it is a non-cooperative game, they're going to be acting in their own best interest, and that's exactly where we get this Nash equilibrium right here. And once again, it is the Nash equilibrium because none of them can do better by unilaterally deviating. If Chris decides to not confess, he gets 3 years in prison. If Mariska decides not to confess, she gets 3 years in prison. So therefore, they can only hone in on this option if they're not allowed to cooperate with one another. Our next step is to go ahead and see whether or not we could do better than this outcome, or what are a few ways we can go ahead and get out of this particular outcome. And it's going to be a little bit easier for us to go ahead and use a few specific numbers using the sort of classical sort of numbering system, using a pricing strategy game, using Walmart and Target. So each of these firms is trying to figure out whether to advertise heavy or to advertise lightly. And as we take a look at this, this is going to end up being a prisoner's dilemma as well. So we go through the entire process. Put yourself in Target shoes, put yourself in Walmart shoes. So if we are Target, we know for sure that Walmart's going to advertise heavy. We're going to advertise heavy. We're going to keep on advertising heavy if Walmart is going to advertise light. And then go ahead, put yourself in Walmart shoes this time around. If you know for sure that Target's going to advertise heavy, you're going to want to advertise heavy. And if Target's going to advertise light, you're going to want to advertise heavy still. So therefore, the Nash equilibrium is going to be where each of the firms is going to advertise heavily, but they end up with 50, let's say, $1 million each. However, we do notice that this is a vastly inferior outcome to something like this one, where both of them decide to advertise lightly, where Target gets 100 million and Walmart also gets 100 million. However, they aren't allowed to cooperate with one another, which is why we end up at this Nash equilibrium right here. What we want to go ahead and do is, how exactly can we get the best or the cooperative outcome in the prisoner's dilemma? So how can Target and how can Walmart come to this outcome, come to this solution right here? Because this is going to be the best outcome for both of these firms, rather than if the game were played out naturally, where each of the firms is going to advertise heavy, leading to this prisoner's dilemma. Same thing in this example. How exactly can we get Chris and Mariska to hone in on not confessing, getting the best outcome for both of them, rather than letting the game play out naturally, where both of them end up confessing and getting a worse outcome? And that's where we make the usage of a lot of repeated games and a lot of trigger strategies. And that's also where we go ahead and take a look at the second type of game, which is going to be a sequential move game. So we'll take a look at the repeated games and trigger strategies next, and then we'll go ahead and see how we can solve this prisoner's dilemma using the sequential game trees that we need to build up as well. I'll see you guys in the next video.